Difan Zhou, Lisheng Chen, and Chuan Gu, who are all at UCLA. Just going to jump into it because I don't have much time. So there's a lot of self-training algorithms. The one I'm going to be talking about is one of self-training with pseudolabelers. So pseudolabelers are just classifiers. It's just a fancy way of saying that, where you generate labels for unlabeled data by just using the output of that classifier. And the procedure that, one of the common procedures for this algorithm is to assume you have access to some small labeled data set and some larger unlabeled data set. And you perform supervised learning on that small labeled data set to learn some initial pseudolabeler. That's what we'll call beta PL. And beta PL is used to generate labels for your unlabeled data. And then you feed in those pseudolabels into like a supervised learning algorithm that uses the unlabeled data and the pseudolabels that came from the prediction from beta PL. And then you run supervised learning, you update the classifier at every iteration, generate new pseudolabels using that new pseudolabeler. And the potential benefit for this is that it allows for you to get away with leveraging these large unlabeled data sets, right? The kind of catch is this going to work? Like, will it actually be able to learn the optimal classifier? And what are the conditions under which we could expect such a thing to happen? So something that's been shown in a variety of vision models and in other settings is that this does actually work. It is able to help improve performance on a number of metrics, especially in vision tests like on predicting ImageNet. And so the kind of question that I'll be talking about is whether or not is trying to characterize the sample complexity of this standard self-training algorithm, both from trying to understand how many labeled examples do you need in order to jumpstart this process, and whether or not you can learn the optimal classifier and how many unlabeled examples you might need to do that. So the distribution that we'll be considering is a mixture model. So we have two cluster means at mu and minus mu. And we assume that the mixture distribution or the cluster distributions are isotropic, rotationally symmetric, and log concave. So in this setting, you can show that the Bayes optimal classifier for the distribution is just the linear classifier given by the taking the output of the sign of the mean dot product with the feature. So we'll want to kind of compare performance of whatever the algorithm is to whatever the performance of that classifier is. This is something just to keep in mind. We have isotropic clusters, and we're not going to make assumptions on the separation between them. So you could have a very high overlap between them, in which case this Bayes optimal classifier is not going to perform very well. Just something to keep in mind. And so here's the kind of gory details of what this algorithm looks like. Right, so we start with some initial classifier beta PL. And at each step, we're going to be performing kind of online SGD with a relatively large batch size. So we have this unlabeled data that's IID at each iteration, generate the pseudolabels using the current pseudolabeler. And then the update that we do is a kind of weight normalized gradient descent. So something I noticed is that we're differentiating through the normalization. And because the pseudolabels are really just the sign of the predictions, you're going to get an absolute value term that appears. Right, so you have kind of two sources of non-convexity, one that comes from the absolute value, one that comes through differentiating through the normalization. And this is an important thing because, because we have this absolute value, if you didn't have any normalization, you could just drive that unsupervised loss to zero just by taking the norm of the predictor to infinity. So some type of regularization seems necessary, and so that's why we are including this weight normalization term. Okay, so we're going on the setup, because next I'll go into what the results are. Okay. Okay, so the main results is that, so in this mixture model setting that I just described, there's some universal constant C error, such that as long as the initial pseudolabeler that you use has a classification error smaller than that absolute constant, then the self-training algorithm that's initialized at that pseudolabeler and using a total of d over epsilon squared unlabeled examples suffices to get within epsilon error of the Bayes optimal error. And so we need a batch size of like order 1 over epsilon, runtime of d over epsilon, and so that's where the unlabeled sample complexity comes from. And so the kind of tagline is that self-training converts weak learners in the sense that you get constant error initially to strong learners, so getting within epsilon of the optimal error using only unlabeled examples. And so you might ask, like, what's the catch? And the catch is, how do you start this algorithm that is able to get that constant error that's necessary to jumpstart this? And that's what our next result will describe. So in order to jumpstart the self-training algorithm on the last result, we do need to have that the mixture models are somewhat more separated, that there's some constant that the mean is bigger than that constant. But again, keep in mind the separation, it's isotropic clusters, so we're not having a dependence on the dimension in terms of separation, it's just a constant. But in this setting, the kind of standard supervised approach for linear classification is just to do standard gradient descent on the logistic loss without any normalization. And if you run this in this setting, then you can output a classifier that has a classification error smaller than that constant. Mm-hmm.
So, first, to get this initial guess is sufficient to take sum over I yi xi, right?
Yes. Yeah. That's
okay. So, and the other question is, what happens if you take a this? I mean, this distribution has the property that if you just look at, you can identify, even if you don't label, if you have infinite samples, you can identify it, right? It's just a principal eigenfunction of the population covariance.
Yes.
Right? But so in that sense, it's kind of an easy case. What happens if you have a spherically symmetric distribution in which there is no of the xi, so there is no signal of the covariance?
Yeah, that's a good question. It's not clear to me the extent to which that's possible. I mean, I'll get into the kind of proof idea shortly, where it might be possible in some settings. But our proof does rely upon the fact that there is this structure of the mixture distribution, and so that allows for getting around it. But I guess also I just want to emphasize that the question is, if you have infinite labeled examples, then yes, the problem's easy. But like, how many labeled examples do you need in order to start a self-training algorithm that can?
If
you have infinite unlabeled,
you just take the covariance.
Mm-hmm.
In fact, if you have d log d samples.
Yeah.
And then there is a spike in the
covariance. That's true. Yes. So I guess it is a toy model for which there are more efficient algorithms for learning it. But I guess the interest is in seeing whether or not this non-convex optimization problem that's used in practice can have somewhat good labeled sample complexity for learning the problem. Mm-hmm.
So I assume that the assumption that the two mixtures, the labels completely align with the two components of the mixture. Right?
Yeah.
Because so basically the answer will already have the information of the label. If I cut it with no align, then I don't think this should work.
Yeah, I mean, I guess it does work in practice in complicated distributions. So I feel like there might be some settings in which there are reasonable distributional assumptions that still result in this behavior.
I guess I'm trying to understand how much the unlabeled data structure has to help you somehow. If it doesn't, then it shouldn't work.
Yeah, I think there has to be some sense in which there is structure to the unlabeled data, because otherwise you can't hope to learn using just an unsupervised approach. Yeah. Okay, and so just the kind of corollary to this result is that if as long as the mixtures are separated by some constant, then this semi-supervised self-training approach can learn the Bayes optimal classifier using a constant with respect to epsilon labeled examples and d over epsilon squared unlabeled examples. So the kind of core of the proof idea, and maybe why I think it might have some, there might be some insight that could be used in other settings, is about identifying that if you can essentially treat, because the problem with self-training is that you have these noisy labels that are generated by a pseudolabeler that does not actually predict the correct labels for the distribution, right? It makes errors with some proportion. But if you can have some algorithm which is tolerant to label noise in some sense, then it should work in the self-training. You should be able to get away with using unlabeled examples in the self-training setting. And so why is that? Is because you can imagine the updates that you're doing in gradient descent are essentially as if you had come from a distribution where there was some true generating process where the labels came from the pseudolabeler, but then those labels are corrupted with some possibly instance-dependent probability, right? So you can just view like initially the labels come as the sign of beta x, and then you flip the sign with some possibly instance-dependent probability, and that's really all that the algorithm is seeing. And so if you have an algorithm which is can be tolerant to kind of label noise, then it stands to reason that you can have some type of self-training algorithm that is able to just use the pseudo labels that come from that algorithm and still be able to learn. And so this is kind of the proof idea. And so we can utilize some proof techniques for learning half spaces with noise using gradient descent to be able to get around the noisy labels that come from the pseudolabeler. And then just one other component is how do you get around the non-convexity? Because we're differentiating through that absolute value sign. We're also differentiating through the normalization. And the kind of high-level idea is that we show that as long as the classification error of the pseudolabeler is smaller than some constant, then you have this kind of proxy convexity property, which essentially allows for you to say that whenever the angle between the predictor and the Bayes optimal predictor is large, then you will get closer to the Bayes optimal predictor. And so this is the kind of the real technical meat of the proof, is to be able to show this type of inequality.
It doesn't seem like the norm of mu is important here. What role does it play in the sample complexities?
It doesn't essentially play a role at all.
So then, this addresses this question about unsupervised stuff.
Yeah, so I guess I missed this is Ben's point about whether or not they're separate enough.
So as you get a weaker and weaker signal from the unlabeled data, you're not seeing that playing a role in the performance of this method.
Right. Yeah, that's true.
So that doesn't have to help. If mu is 0 or close to 0, then there's no information from the unlabeled.
That's right.
Right. I mean, we need to have mu as at least some constant in order to jumpstart the supervised learning, so that this constant is like, say, like 1/10. This like there is some. It requires there to be some separation, but like a constant level of separation is sufficient. But a constant is pretty small when you're considering isotropic models. Right.
Okay, so it's in there.
Yeah, it's kind of hidden in here, and that's what the supervised claim was about. Okay, I guess I'm about done. Yeah, so just something I'm just interested in exploring after this is whether or not this idea that designing or having analysis of algorithms that are tolerant to label noise can lead to guarantees using unlabeled data, and whether or not the kind of very strong structural assumptions that we make on the joint distribution, whether or not those can be loosened in some way in these other algorithms that we know are able to tolerate label noise.
You probably don't need it to mu, right? 1, 2.
I think it's likely. I haven't worked out where the error would, what that error would from our proof would introduce. I think it probably, as long as there's some separation, then I think it would probably be fine. Okay. And then that's my talk.
So maybe 1 or 2 questions.
Maybe by far, but how do you compare this with boosting? You're kind of boosting something, right? You have weak learner, and then but you're using unlabeled data to boost. Is there any connection at all?
It's possible because we're not really like combining the fact that we're not really combining weak learners to make a strong learner. It's more that the weak learner itself, like as long as the classification error is small, then you have this kind of nice optimization landscape that allows for kind of ignoring the label noise, basically.
But what if actually I do combine?
Yeah, I'm not sure. I'm not sure what that would look like, but it could work, and I'm not sure.
I mean, in theory, the unlabeled data is also making the weak learner better, right?
Mhm.
So if I combine on top of that,
Yeah, I'm not sure what it would look like, but I think it would be able to get something tractable out of that.
Questions?
So I think related to the previous question.
Yeah, so related to the previous question, are there connections to perhaps doing like something like weak transductive learning followed by just supervised learning? So if you have a weak transductive learning guarantee or unlabeled labels on the unlabeled data are good enough. Like, are there connections there?
I'm
Some
not
techniques?
sure. Yeah, I haven't thought about that. I'm not sure what it would look like in this setting. Like,
Okay.
yeah, sorry.
Yeah, we can chat offline.
Okay, let's thank Spencer again. Session. Lunch break now.